Okay, so in the last video, we looked at introducing the idea of area, and we looked at two particular types of quadrilaterals. By quadrilaterals, I mean four-sided shapes, and we looked at a rectangle and a square. Now, today we're going to look at a special type of quadrilateral, a slightly different one. We're going to look at the parallelogram here. So, a parallelogram, we have a four-sided shape with opposite sides being parallel. And it almost looks like a squished over slanted rectangle here. So I'm just going to show that these are parallel by showing these little symbols. Here they tell us that something is parallel. And we want to find the space, the area, which is taken up by this particular parallelogram. Now, before we even go into that, we want to just observe a special feature of these types of parallelograms. Now, it's kind of hard to tell right off the bat, and intuitively you'd want to say, well, I know that for my other quadrilaterals, I just multiply this by this. Cool. But with parallelograms, they work a little different. Now, let me just make a slight alteration to this shape here. I'm going to just draw something, and I'm just going to draw something on it, a couple of things, and we're going to note any sort of observations we can make. And I have a program which will also make this a bit easier to see. So I'm going to draw a straight line from this edge, this top edge. Oh, that's not quite straight, but a straight line here. And this straight line is going to be what we call perpendicular to our two sides here and here. So, perpendicular, we mean that if you watched the videos on angle geometry, they essentially just make a 90-degree angle here. So, we've made a straight line going from this top corner all the way down, which is perpendicular to these two sides. And I'm just going to shade in this area here. We have this little triangle here. We have this particular area. Now, from another corner, let's say this one up here, I'm going to draw that same straight line down. To here and across. And this is also going to be perpendicular. So if, for example, this were to extend, if this imaginary line were to extend, we would have this new one I drew in purple as perpendicular. I'm going to also draw this all the way across. Now, what do we notice about, and I haven't drawn it super well. I'm pretty shocking at drawing, so just bear with me for a minute. I do have a good example to show you as well. But what do we notice about these two areas I have shaded in? Could we say, just by observing, if I were to say, take this yellow triangles area, and we'll go into area of a triangle later. We don't need to know the exact formula for it, but just by observation, this yellow triangle, if I were to take this shape here and slide it across, it looks like, just by looking at it, that it would fit almost seamlessly into this spot here. So just shifting this yellow one to this yellow one, what shape do we get? Well, we're left with a rectangle, aren't we? So, and this essentially doesn't matter as long as we've kind of drawn this line. it doesn't matter where we do it, because an inherent feature of parallelograms is that we can kind of chop up one bit of it, slide it across, and we will make a rectangle. Let me show you an example on another tab here from GeoGebra. Now, well, this isn't going full screen, but that's okay. Now we are going to slide, we're going to essentially draw this line down here, same way we've done, and you can see this area on the left here, this kind of segment that's cut out. That is going to seamlessly fit next to it. And the same areas are there, but just when we cut our parallelogram and shift certain bits around, we will always get a rectangle. So from here down and across, we get a rectangle. Now, going back to what I've drawn here, couldn't we then say, well, if we have a perpendicular height, we're going to call it, here. So I'm going to write perpendicular height and a width down the bottom. Let me write that in purple. And a width. The area we get is essentially, for a parallelogram, all right, here, area of, I'll just write PAR, short for parallelogram, equals the perpendicular height, because this perpendicular height makes up the rectangle we formed, well, one dimension of the rectangle, and the original width, and it doesn't matter if we take it from here to here, or when we slide it across from here to here, that remains our width. You can even see it over here. Our width doesn't change. We just make this cut, but the width is a constant, isn't it? So the area of our parallelogram is our perpendicular height, I've got my T there, multiplied by our width. So in a lot of questions you may encounter, you will be given these dimensions. So I'm going to rub out all this stuff that I drew, so we're left with the original parallelogram we had. Now, say I have a parallelogram, just to give you an example, with a perpendicular height of 5 meters and a width of 4 meters. What would be its area? Feel free to pause and have a go, but what we should get is an area of 5 meters multiplied by 4 meters. And we showed here that when we deconstruct our parallelogram, we essentially get the features of a rectangle. And how did we find the area of our rectangle? Well, we multiplied the lengths as well as the units. So here we end up with 20 meters squared. Thanks for watching.